We start off the semester in Chapter 2. Chapter 1 is just a review of some pre-calculus concepts. A lot of the calculus concepts we're going to learn this semester are defined using limits. So here in Chapter 2, what we're going to do is we are going to learn about what exactly a limit is and how we calculate limits. And there are three main ways to calculate limits. And what exactly to do we do when we get some of the more complicated limits. So some calculation techniques and some strategies to deal with the more difficult ones. The very first section here is really it's just a short section. It's just kind of exploring the idea of what exactly a limit is, and we're going to do that by looking at a specific application, and that's the difference between instantaneous velocity and average velocity. Now, average velocity is an algebra concept that you may have learned before, and it really just boils down to slope. Instantaneous velocity is a calculus concept. And instantaneous velocity is something that we are going to talk a lot about once we start talking about derivatives. And the definition of a derivative requires us to know how to do a limit. So that's why we spend this whole first chapter talking about limits. So we're going to look at a specific example, and one of the best ways to describe this is with a graph. So I'm going to start with the graph of f of x equals x squared. And let's say that just the right-hand side of this graph is plotting our distance over time. So we're keeping track of how far we've traveled over time. To calculate average velocity, so throughout this problem, what I want you to keep in mind is if you were driving somewhere, if you were to compute your average velocity, you would determine how long it took you to get somewhere and what the total number of miles were that you drove. So our average velocity has to do with totals. So it's our total distance over total time. So if we wanted to do this from maybe start to finish, we would say, okay, I took this total amount of time to travel this total amount of distance, and if we connect those 2 points, what we have just drawn is a secant line to that graph. Now, a secant line is a line that crosses our graph in 2 places. Now, we can easily compute this with things that we know from algebra, because we will know 2 points on this graph. And this is just our slope formula. Now, where this changes into calculus is if we just want to know instantaneous velocity. Instantaneous velocity is, again, if you think back to the driving analogy, if at one point in that driving trip we want to look down at our speedometer and see what exactly our speedometer says at that exact moment in time. So it's our velocity at t equals, I'm going to say A. It's just at one specific moment in time. So I'm going to say t equals A. So if that's time A, I want to know how fast I'm going at that exact moment in time. So we only know one point on the graph in that case. So we can't use algebra. We can't do the slope formula. Slope formula requires 2 points. So if we were to do a line here, it's called a tangent line because it only touches the graph in one place. And this requires some calculus in order for us to calculate the slope of that line. Now what we can do is we can use limits to help us turn our secant line into our tangent line. So I'm going to draw a new graph and I'm going to make a little chart to show you exactly how we're going to do this. And our progression through the chart is actually how we do limits. It's one of our techniques for doing limits. So I'm going to blow up just the piece that we're interested in. We're going to try to figure out, so this is going to be our example. We're going to use secant lines to determine the slope of the tangent line on f of x equals x squared at x equals 1. So I'm only going to draw the piece that I need. So this is our x squared graph. There's 2, 4. There's 1, 1. There's 0, 0. So those are some different points that f of x equals x squared goes through. We want the tangent line. We want the slope of the tangent line at the x equals 1. So what we're looking for, and I'm going to draw this tangent line. I'm going to see if I can draw it a little bit nicer. Oops. Maybe. See if I can move it a tiny bit. I wanted a different color. I'm just going to draw it. I want the slope of this tangent line. The problem is I only know one point. So we can't use algebra to do it. So this is what we're going to do. We're going to try to approximate it using secant lines. So I'm going to make a chart here of x and y coordinates. And my original point is 1, 1. This is our goal point. This is where we want our slope. What we need in order to use algebra is a second point. If we have a second point, we can calculate slope. So I'm going to pick a second point on that graph. So another easy second point would be 2, 4. So if we connect 1, 1 and 2, 4, we can see that that's definitely not the tangent line. It's kind of similar, but that's a secant line. So if we use 2, 4, and if we do the slope between 1, 1 and 2, 4, remember the slope formula is m equals y2 minus y1 over x2 minus x1. So the difference in y's over the difference in x's. So it's going to be 4 minus 1 over 2 minus 1, which is 3. So the slope of this red line is 3. But we can tell that those two lines are definitely not the same. That red line is definitely too steep. So what happens is what we want to do is we want to pick a point that's a little bit closer to our goal point. So I'm going to move closer. The point 2, 4 was a little bit too far away. So I'm going to move closer to 1, 1. I'm going to go to 1.5 for my x coordinate. To get the y coordinate that goes with it, you need to go back to your function because we're picking points on the function. So if x is 1.5, to get y, we're going to square it. 1.5 squared is 2.25. And we're going to do the slope between 1, 1 and 1.5, 2.25. Now, if we draw this green line, it's still a secant line because I'm using 2 points on the graph, but you'll see this is closer to the blue line. The blue line is the tangent line. So we're going to do the change in y over the change in x. We get 1.25 divided by 0.5, which is 2.5. So we're getting closer to our goal point, and I'm going to do one more. I'm going to get closer again. This time I'm going to get all the way down to 1.1. So now I'm really, really close to the goal point. And if I connect the goal point with my second point, and again, we need a y coordinate, and we are on the function. So if I plug 1.1 into my function, 1.1 squared is 1.21. And if I connect them, wow, that one is really close to my blue line. They're very, very similar. And if I do the slope formula, 1.21 minus 1 over 1.1 minus 1, I get 0.21 divided by 0.1, which is 2.1. We are trying to figure out the slope of the tangent line. So we're figuring out the slopes of some other lines that are getting closer to it. So what we're trying to do is recognize a pattern in these slopes that we see are getting closer to the slope of our line. This is what a limit is. The limit is when we don't necessarily know the answer that we're looking for, but we're looking at a pattern of numbers that we know are approaching our answer. I know that these slopes are getting closer and closer and closer to our answer. So we're trying to figure out what our answer is going to be, the slope of our tangent line at 1, 1, based on where it looks like these guys are going. Now, just based on these numbers, you can't always get an exact, definite answer. We will have a way later on in the chapter to get an exact, definite answer, but sometimes numerically you can't get an exact, definite answer. It's just a guess. So remember, that black line was the best one. The red line was pretty far away. The green line was better. The black one was the best one, and it was really, really, really close. So it looks like my guess would be it's going to be about a slope of 2 would be my guess. And if you want to, I picked points that were to the right of 1, 1. We could do this again and pick points that are to the left of 1, 1. We could pick 0, 0, or a half, comma, 0.25, or 0.9, 0.81. And we can make a second chart, and we can approach 1, 1 from the left and see how these slopes are approaching from the left as well, and see if they're going to come up from 2 as well. But based on the calculations we've done so far and the graph that we see with these secant lines approaching our tangent line, it looks like the slope of that tangent line is going to be 2. So this whole process right here of taking some values that we can do and using them to make a prediction of one that we can't do is a limit. So I've got a neat little graph I want to show you. And I have posted the link for this on our Moodle page. And I think I put it under resources. This is the graph of x squared plus 1. And this just kind of shows you how we can move a secant line to make it match up with a tangent line. So on this one, the blue line is the secant line and the green line is the tangent line. So we can put A is where we want the tangent slope at. So I'm going to say that I want to know the tangent slope at 2. So the green line is our tangent line, and that's what I want to know the slope for. For the blue line is our secant line, and the secant line always uses 2 points on the graph. So it uses your goal point and a second point. And as we drag that second point closer and closer and closer to the goal point, the secant line eventually gets closer and closer and closer to the tangent line. And it doesn't matter whether it approaches from the left, it'll get closer and closer and closer to the tangent, or if it approaches from the right, it'll get closer and closer and closer to the tangent. And we can move the A point, we can do this at any point. So if I want to know what the tangent slope is at 0, I can approach from the left and get closer and closer and closer to my goal point until my secant line matches my tangent line. Or I can approach from the right until my secant line gets closer and closer and closer to my tangent line. And we can actually work out all the calculations for this because we know the function. This is the graph of f of x equals x squared plus 1. We can identify the point where we want the tangent slope. Where I have it set up right now, we want the tangent slope at x equals 0. So that would be the point 0, 1. So what we need is a second point, which is our B point. And we would just start picking random points that get closer and closer and closer to 0, 1 and try to identify where it looks like they're approaching. And that whole process is a limit to pick points closer and closer and closer until we can figure out what value they are approaching is the process of finding a limit. So really, there's not a whole lot for you to do in this section besides just observing. and kind of seeing exactly what a limit is, you will, sorry about that, have a lot more chances in the sections to come to learn how to do these limits either graphically or numerically or analytically, which are 3 different methods for calculating limits. And we'll learn lots of different techniques because, of course, some of them are going to have little tricks and some of them are going to work out nice and easily. But this is 2.1. So I encourage you to go to that website and play around with the graph. And there will be a couple problems in the homework where you will have to compute some secant slopes and use them to try to make a guess at what a tangent slope is going to be.